Hi class, we are now on 10.4b, gas laws part 2. So the pressure, the volume, and temperature of an ideal gas are related to each other through simple mathematical relationships called the gas laws. These relationships are very useful to describing common gases. In the last lesson, we looked at Boyle's law, Charles, and the combined gas law. In this lesson, we're going to look at Avogadro's law and the ideal gas law. We will also look at mixtures of gases and consider a molecular explanation for the gas laws. So Avogadro's law. So not just now we're going to look at something we learned Avogadro's number. Now we're going to look at Avogadro's law. It states that if pressure and temperature are constant, the volume of a gas is proportional to the number of moles of gas present. The more gas is present, the larger the volume it occupies. Mathematically, we can say that the volume, which is V, is proportional to the number of moles of gas, which we represent with the letter N. The exact volume that a mole of gas occupies depends on its temperature and pressure. A temperature of 0 degrees Celsius is 273 Kelvin, and a pressure of 1.0 atmospheres is called standard temperature and pressure, or STP. So at STP with these conditions, a gas occupies a volume of 22.4 liters. This is about the volume of a large helium balloon. So for instance, you'll get problems that will say at STP or standard temperature and pressure, but won't provide the temperature and pressure. This is what they mean. They mean these specific conditions of temperature being 273 Kelvin and pressure at 1.0 atm. Excuse me. Okay, and now we're going to look at the ideal gas law. The gas laws described so far allow us to relate different properties of gases. We can connect all of these together using the ideal gas law. This extraordinarily useful law relates the amount of gas present to its pressure, volume, and temperature. We usually write this law as PV equals nRT. Pressure is P, V is volume, T is temperature in kelvins, N is the number of moles, and R is the gas constant that ties everything together. And this is a value of 0.0821 liters per atm over moles per Kelvin. When using the ideal gas law, it is important to make sure that the temperature is expressed in kelvins and the units of volume and pressure align with the values included in the gas law. For instance, in the gas law, we have liters and atmospheres, so your numbers, your values for those which your volume and pressure have to be in those values. So let's take a look at a problem. What volume does 1 mole of gas occupy at temperature 0 degrees Celsius and a pressure of 1.0 atmosphere? So we take the PV nRT and then we isolate the variable that we need to solve. In this case, it's volume. So then we plug in everything. First, we make our conversion. So temperature is 273.15. And then we plug it all in. So we have, for the moles, it's 1 mole. For our gas count, that never changes. We're going to keep that. The temperature's plugged in, and then we have our pressure on the bottom. And that ends up giving us a volume of 22.4 liters. And that, what was not specified here is, I had just discussed that this and this pressure, these are standard temperature and pressure. It just didn't say it in this one. Okay, so mixtures of gases and partial pressures. We commonly encounter gases that contain several components. For example, air is a mixture of gases composed of about 78% nitrogen and 21% oxygen. The remaining 1% is a mixture of argon, carbon dioxide, and water vapor and other trace components. Fortunately, when dealing with ideal gases, the pressure and volume depend only on the amount of gas present and not the identity of the gas. 1 mole of oxygen gas has the same pressure and volume as 1 mole of nitrogen gas or 1 mole of carbon dioxide. So let me repeat that again. When dealing with ideal gases, the pressure and volume depend only on the amount of gas present, not on the identity. 1 mole of an oxygen gas has the same pressure and volume as a mole of nitrogen gas, as a mole of carbon dioxide gas, etc. When working with mixtures of gases, we sometimes use partial pressures of the gases that are present. The partial pressure is the pressure caused by one gas in a mixture. We can add up the partial pressures to find the total pressure of the mixture. So what this means is that every gas on their own has their own pressure in that container. And what you do is you determine that specific pressure for that container, and then you do the same thing for any other gases, and then you add all those up. So that's why they call them partial pressures. You add them all up at the end, and there's an example we'll cover. So if a 40.0 liter cylinder is filled with 5 moles of nitrogen, 2 moles of oxygen, and 3 moles of carbon dioxide at a temperature of 400 K, what is the pressure inside the cylinder? So there's two approaches that we could take to solve this problem. The first is to calculate the pressure that is produced by each of the individual gases, the partial pressures, and what we could do is calculate them like this. So we can isolate, and then you make sure you denote that this is the pressure you're looking for this one. And what you find is that you see the variables for the rest of them are all the same. The only difference is actual mole amount. And then you end up getting the partial pressure for nitrogen, the partial pressure for oxygen, the partial pressure for CO2. When you add them up, it gives you the total pressure of the the total pressure of that vessel. So in this case, this is one approach of how to do that. This is a pretty good way. This is actually how I do it. I separate them out and then I add them all together. But there is another way to do this, and it simplifies the calculation because the total pressure depends on the number of moles of the gas. So we can find the total number of moles present and then calculate the pressure based on that. So this is actually a simplified way. I understand that it's simplified, but I didn't learn how to do these calculations this way, so I don't do them this way. I do it the longer way. So you take the 5 moles of nitrogen, the 2 moles of oxygen, and the 3 moles of CO2, and that equals 10 moles. You can now plug that in to get the total of the pressure of the vessel, and it ends up being 8.21, which also matches this amount. Okay, so over the last couple of lessons, we used mathematical relationships to describe how gases behave. By thinking about gases on the molecular level, we can begin to understand why these mathematical relationships are so, and we can also predict the behavior of gases in other situations. Let's ask 3 questions about the relationship between the particles in a container and the pressure they exert. 1. How does the pressure change if the temperature of the gas increases? At higher temperatures, the particles move faster. Faster moving particles strike their surroundings with more force, exerting more pressure. On the other hand, if the temperature decreases, the pressure drops. A perfect example would be leaving something in your car that has gas in it. And if it gets really hot, it'll pop open or explode. A soda can, for instance, if it's hot and it's left in your car and the heat is really, really hot, the temperature goes up, obviously, and the gas, the CO2 that is in the soda, will burst. It'll pop open, and that doesn't tend to happen on a day that the temperature is cool. What happens to the pressure of a gas if the volume increases? And these have to do with the laws. So look at the laws: Boyle's law, Charles's law, combined gas law. These tell you, remember, one is inverse. If it goes up, the other goes down. The other one's directly proportional, where it means if one goes up, the other goes up. So these questions are matching what you've learned. What happens to the pressure of a gas if the volume increases? If the volume of a container increases, the particles have to travel farther before reaching the walls of a container. As a result, the particles collide with the container less frequently. An increase in volume produces a decrease in pressure. So if you think of a soda can and it's got CO2 in it. Now pretend you can magically take the top of it and elongate it, make it really long. Now the pressure decreases because it's not so compressed. You've actually increased the volume where the CO2 molecules can move. And what happens to the pressure of a gas if the number of particles in a container is increased? If you've ever pumped up a tire or basketball, you know that increasing the amount of gas particles present increases the pressure. So on a molecular level, more gas particles mean the particles will strike the sides of the container more often and create pressure. So now let's take a look at some problems. So again, here is the ideal gas law. Temperature must be in kelvins. Pressure and volume units must match the gas constant. Basically what happens is that we use this gas constant and it'll cancel all the variables that we have except for the variable we're missing and leave that unit, which will be in our answer. So if you do it right, that's a good way to catch that. What is the volume of a 0.250 moles of oxygen gas at 19 degrees Celsius and 775 torr? One thing I want to point out here, remember, oxygen gas, it's not telling you, it's not showing you the chemical formula. So if you put this as not a diatomic molecule, your answer will be wrong. Remember, oxygen gas, there's two molecules to be considered oxygen gas. So what I do is I pull everything out, and then in this case, I showed you the conversion. I'm not going to show that anymore of how to do that. But here is the conversion. I always leave more numbers than I need. And then I isolate the one I need, which is volume. I add this in, and then, oh, you know what? I apologize. For this, there's a problem coming up where we're going to need to know the molar mass of this. In this case, it doesn't matter. But if you had to write it out, this is O2. This is not O, it's O2. And then it's going to give us the volume, and the volume is 5.9 liters. You see where I left it, and then you can see where it's rounded. Okay. A mixture of oxygen, nitrogen, and carbon dioxide gases is placed into a sealed flask. The mixture has a volume of 2 liters and a pressure of 1.25 at 23 degrees Celsius. What is the total number of moles of gas in the flask? So now we're going to isolate for moles. We're going to pull everything out, and then we're going to plug it in. And remember, it doesn't matter what the gas is. And in this case, it is telling us the moles. So it's got a mixture. Excuse me. So in this case, we have a mixture in here. It's giving us the total amount of moles. We didn't have to separate anything out. We didn't have to worry about any of that part. We just had to figure out the total amount of the moles that are in this vessel, and they've given us the information. What is the mass of nitrogen gas at STP that has a volume of 1.00 liters? Okay, so remember when I said that STP has certain conditions? It is implying that the temperature is at 273 and the pressure is at 1.0 atm. It will not tell you that. The fact that you're supposed to know what STP means. So I pulled out that information. Now, this is one that is a little different than what we've covered, but it's not really that difficult, and I've even highlighted, it's just done in 2 steps. So let me go over this. It's asking for the mass. So what we've shown you in the past is that we can get the moles, and then all we have to do is one more step with whatever the identity of the gas is using the molar mass. The moles will cancel out, and it'll give us grams. So this is not a difficult problem. It's just something that's just one more additional step. So in this case, we plug everything in that we have. We have our pressure, we have our volume, we have our gas constant, and we have our temperature. That gives us the moles of gas of nitrogen, but it's asking for the mass. So now we're going to use the molar mass. And remember, nitrogen is like oxygen. It's a diatomic molecule. So just writing one N is going to change the molar mass to 14, and your answer would be wrong. It's a diatomic, so you have to have 2 of them, which gives a molar mass of 28. So if we can take that number down here. We use the molar mass of diatomic nitrogen, and it gives us a 1.249 grams, and the answer is 1.25. Okay, so which of these is predicted by the gas laws? I'm just going to jump ahead. And cooling a gas at constant pressure will cause the volume to decrease. Once you learn the laws, then you should instantly be able to determine, okay, this is what happens with that. That goes with that law. What is the density? Now, this is a problem that tends to mess students up. And notice there was no samples in the lecture that I did. For some reason, they didn't give that to me. But I have broken this down. This is not a difficult problem. What is the density and it tells you what the units have to be. And that helps you because it'll keep you on the right path. Of 1 gram of methane at 15 degrees Celsius and 745 millimeters mercury. This one can be a little confusing, but once you look it over, once it's been completed, hopefully it makes more sense. So I went online And I found a slide somebody had put up, and this is exactly what we're going to do. We're going to solve it this way. You take the PV equals nRT, and then we're going to isolate N. And N in this case, we take the mass and the molar mass, which will give us the moles, right? Because if we have grams up here and then we have grams per mole, the grams will cancel out. But I'm just trying to show you what this means at this point. So we have our mass, which would be this, and we have our molar mass, which would be this. So we're going to take this and plug this in where N would be. And that's where N is. See, N's here, N's going to go here. Now, if we move this around, it's asking for density. And what is density? Density is mass over volume. We have a V and we have an M. So if we move this around where we isolate the M and the V, and then we have the P, we have the molar mass, which is capital M, we have the R and the T. But if we look at that, that is density. So by plugging in everything that we have, we can determine the density. So in this case, you have M and we have V. So I take my pressure, there's my pressure, here's my molar mass, here is my gas constant, and here's my temperature. And what I did is I very badly, as you can see, used the drawing part of the PowerPoint, and I canceled out the units because I expect them to be in these units which match this, and they do. And then this is the final answer. So this is not a difficult problem. You just got to move things around and maybe substitute a little bit. Something that if you've been doing the same kind of calculations, you forget. Okay, a flask, a 2.50 liter flask at 25 degrees Celsius contains 5 grams each. So it's got 5 grams of oxygen, 5 grams of nitrogen. What is the total pressure of the gas within the vessel? So I even wrote this out to help you guys understand how to do this. This matches the problems that we showed you. I showed you previously. We got to determine the moles for oxygen and nitrogen. We separately determine the pressure for each, and then we add the pressures together. I don't do it the quick way. That's not how I learned. So first thing I did is I determined the moles of oxygen, and then I plugged it in to solve for the pressure, the partial pressure of oxygen. And I did the same thing for nitrogen. So you see these numbers are different, and I just realized that I messed up on this number here. This number's wrong. This number, I will fix it on the PowerPoint, but this is wrong. This number, it is correct here. So I did an extra 1 and I missed the 6. So kind of cross that out. But here is the numbers. We have our partial pressure for oxygen, our partial pressure for nitrogen. I add them together, and it gives me the final answer. A flask contains liquid water and hydrogen gas at 22 degrees Celsius. The vapor pressure of water at 22 degrees Celsius is 19.8 millimeters mercury. If the total pressure of the gas within the flask is 765.0 millimeters mercury, what is the pressure of the hydrogen gas? So this is a partial pressure problem, but let me explain what's happening here. We have an enclosed vessel, a closed up vessel. It has liquid water. It has hydrogen gas on top of it. But the thing is, there's water vapor in the air, and water vapor is gas. We want to know the pressure of the hydrogen gas only. But the problem is we can't separate the vapor water from the hydrogen gas. We have to account for that, because this is we only want the hydrogen, but we have to figure out how to get rid of the water vapor total. Because if we look at the total pressure of this, it's going to give you the value that has added both of these together. So basically we're going to subtract one of them and determine what the other gas is. So here it tells you the total pressure of this vessel is 765.0 millimeters mercury. In this sentence, which I underlined, the vapor pressure of water at 22 degrees Celsius is 19.8 millimeters mercury. Now, this is telling you everything you need. They have a chart, and the chart will tell you vapor pressure at different temperatures, and the vapor pressure of water at different temperature changes. So at 22 degrees Celsius, vapor pressure of water is 19.8 millimeters. So that's the number we're going to subtract to determine the actual partial pressure of the gas. So in this case, here's our vapor pressure, here's our total pressure. So if you do this as